So here's the phase diagram for that copper-nickel system. We plot, again, along the x-axis, the concentration of nickel. So we have pure copper at right, pure nickel at right, and pure copper at left, pure nickel at right. And our y-axis is temperature. This is a binary system. We know that because there are just two components. Those components are copper and nickel. This phase diagram is specific to the condition of 1 atmosphere of pressure. And so as pressure were changed, we would need to evolve the territories on this phase diagram accordingly. And other phase diagrams for different pressures are available and tabulated in resources like textbooks and literature. Okay, so we've also learned by looking at all the areas in this phase diagram that we have phase fields. We see that there are 3 different phase fields. There is the blue phase field, there is the green phase field, and then there is this white sliver territory that is a separate phase field. Okay, so a phase field is represented by one chemically distinct material. Okay, so let's just erase that so we can clean up and look at some of the details. Good. We've also seen that these 3 phase fields are explained by 2 different types of phases. One is a liquid where we have molten metal, like we have up in the green territory here. And that molten metal can, in very high temperatures, exist across all compositional ranges of nickel in copper. We also have an alpha phase. So this is a solid. It is a mixture of the 2 metals. So we use the word solution like we've learned before. And it is a solid based on face-centered cubic packed metal. And at lower temperatures, near 1,000 degrees, this solid, alpha phase as it's called, can exist across all compositional ranges of nickel and copper. So that is, in the face-centered cubic packed arrangement of metal atoms, increasing amounts of nickel would occupy those metal sites as we walk from to the right across the x-axis. Okay, and then in the middle we have a 2-phase area or phase field that has both of those materials present. It has both the liquid molten state with disordered metal atoms at some mixture value of nickel and copper, and we're co-hosting in that little particles of this alpha solid. So a bit like sand particles in water. The sand represents the alpha solid phase, and the water represents the molten liquid. And those can coexist in this white sliver territory. That is a phase field represented by the white area. Okay, the boundaries that take us from outside of the 2-phase liquid phase field area are given some special names. So the Liquidus line is the line that separates the liquid from the 2-phase field area defined by alpha and a liquid. The Solidus line also acts as the line that separates the alpha phase from the 2-phase area that is alpha and liquid. Okay. So these Liquidus lines are alike to the solubility limit that we had a moment ago, and likewise for the Solidus line. Very good. Okay, so to help us picture what we have, we knew in the molten state that we would be homogeneous and the nickel and the copper would be randomly located in this molten, flowing, disordered, random location of all metal atoms. So we might just cartoon that as a green uniform circle. In the FCC solid, we learned in earlier chapters that we have grains of pure metal and there would be packed rows of atoms. In this case, they're face-centered cubic, and that these rows and perfect arrangements of atoms would be separated from a different orientation of that same lattice by a grain boundary that separates the two different orientations of the same FCC lattice. Okay, so that's what we see in the diagram. Some phase diagram, or some grain boundaries separating grains of an FCC lattice where the metal atoms are populated by nickel and copper dependent on the composition. Okay, and so therefore in the middle, as we said, we're going to have liquid coexisting with little particles of the solid alpha. Okay, so some additional things that we've learned. We said that the system was a binary system, so there are two components, copper and nickel, and we know from Hume-Rothery rules that we can expect isomorphous materials, so we can expect complete solubility of one component in another, which means that no matter where we go on this morphology, on this phase diagram, we will never find pure nickel, nor will we ever find pure copper. We always have some mixture of the two. Okay. So how else can we use these phase diagrams? Let's look at a couple of rules that we can think about. Well, rule one might be the condition where if we know the temperature and we know the overall bulk concentration of nickel in the sample, that we can say a few things. Okay, so this C naught is the bulk concentration of nickel in weight percent. What can we say? Well, as an example, if we were at point A, defined by temperature of 1100 degrees C and 60 weight percent nickel, that we would be right here at that point of interest. And we know that this material is going to have a morphology like we've seen before for face center cubic metal that packs perfectly until we reach a grain boundary, and then that same face center cubic metal is found across that grain boundary, and the composition of the metals in that arrangement is balanced and represented by the 60 weight percent value that we have. There is only one phase present, and it is the alpha phase. Okay, take, for example, point B. Point B, we are in the area between the liquidus and the solidus. We are in a two-phase state, so we have both liquid and alpha present. Okay, so we can use the coordinates for a point of interest to report the number of phases present, is what we've learned here by rule one. Good. Rule two, what else can we do? Let's look at a zoom in of that phase diagram. So notice that we're starting at 20 and ending at 50. So we're in the rightmost area, we're half-half in metal by weight of nickel and copper. And rule 2 tells us that if we know the temperature and the concentration of the bulk specimen, so the total thing, all averaged all over the whole specimen, that we can determine the composition of each phase. So what did we learn from that? Let's consider a couple of options. So consider point A up here now at an upper temperature above 1300 degrees C, roughly 1320. We know that the liquid is molten, and we could ask the question, what is the composition of nickel in this material? Well, it's a liquid molten state of the two combined systems, and it's going to have an overall nickel concentration that perfectly matches the x-coordinate for the point A of interest. Okay, so we already know one phase only liquid, and the concentration of nickel in that liquid is 35 weight percent nickel. Take another point here. Let's go down to the solid area. So let's consider point D. Point D, we also know that that's only got one phase present. It's now a solid represented by alpha for the face center cubic option. And the concentration of nickel in this solid, that is represented by the alpha symbol, is also 35 weight percent. So overall, the solid is the little regions of the overall bulk system would overall average to 35 weight percent nickel because we're only one phase. Okay, What else can we do for the area now in between those two easier spots? That is the area that is heterogeneous and represented by both liquid and alpha phase. So there are two phases present in this phase field. And let's consider point B, represented by coordinates TB and, of course, C naught of that same 35 weight percent overall nickel content. To help us answer this question, as what is the composition? How much nickel is in each part? So recall that diagram where we have nickel and little particles of alpha. So the overall area there is nickel is liquid, and these areas are the alpha. What is the composition of nickel in these areas? That is the question. So to do this, we are going to apply a tie line. So a tie line is a horizontal isothermal line, so it's going to be parallel to the x-axis, and it's going to be in a two-phase region, and it will stop. It will terminate once we reach a phase boundary line. Okay, so a tie line for part B must be parallel to the x-axis and proceed in the white space and end when we reach the blue line, the Solidus, and meet likewise to the left, the Liquidus. So here is our tie line. So to determine the concentration of nickel in alpha or in the liquid, we are going to use the tie line to help us. What we do is walk from the point of interest B to our boundary. Okay, so we've walked all the way to the liquid boundary now, and we report the x coordinate for that point. The x coordinate for that point is 32 weight percent. So we now know that the liquid surrounding all the alpha particles is 32 weight percent nickel. Similarly, to understand how much nickel is present in the alpha particles, we'll start at point B, walk to the boundary limit, the Solidus, and then walk down to determine that coordinate. So in this case, we are 43%. So that is the alpha particles that are present. We know they are higher in nickel content, and they are 43 weight percent nickel. Okay. The overall sum, the whole sample, all summed together is 35 weight percent nickel. So kind of interesting that we can develop higher nickel content phases balanced with lower nickel content phases that ultimately average out to give the 35 that is the sum of the total object. Okay, a tie line has taught us that. So again, recall that we've used the intersection points to help us there. Okay. What else? Well, as it may have been curious to you a moment ago, we saw that we have in our material, we have little particles of alpha that are higher in nickel content than the liquid, and the overall sum was essentially weighted average determined by a special technique. Okay, so let's see how we can determine the weight fraction, how much by weight of the specimen is in the alpha state and the remainder is in the liquid state. So we're going to determine the weight fraction of each phase in the white territory, the phase field represented by the white area in the zoom up of the phase diagram. Okay, we're going to use the tie line again for that. So, starting with some easy ones first, let's consider point A. What is the weight fraction of the liquid at point A? Well, there's only one phase, so the weight fraction there has to be 1. Okay, so a weight fraction has to exist between the limits of 0 and 1, and if we only have one phase, the weight fraction of the liquid is at the upper limit. It's all of the material, it's 1.00. That means that there is no alpha phase present. We already knew that, and therefore we assign there a weight fraction value of alpha equals 0. Similarly, going to another easy spot, down back into the solid territory, what do we know about the weight fraction of the liquid down there? Well, there is only one phase and it's not liquid, it's solid. So the weight fraction has to drop to the lower limit of 0, while the only phase that's present is the alpha phase, so that'll now rise to the upper limit of 1 there. Okay, now the more difficult areas, those intermediate zones, let's touch on that. So what is our method for determining the weight fraction in these two-phase regions? The exercise is a bit like a balancing exercise based on the amount of these particles within the other. Okay, and so a way to consider this is, again, we're starting and we know we're at point B, material of interest B. We know the overall content, the whole thing, is 35 weight % nickel. And let's see if we can determine the amount, the composition of nickel in one of these phases. Okay, so let's start with the liquid area, the green. How do we determine the amount of green by weight relative to the total? So the weight fraction of L. We'll use the tie line, but we'll use the length of the tie line segments that are defined by the blue and green, as you see here. So to determine this, we'll note that to go from B and to determine the weight fraction for L, we're going to actually walk to the opposite phase in a direction perfectly parallel to the x-axis. Okay, so let me say that again. It's tricky. We need to walk to the opposite phase to the material of interest. So we're interested in reporting the weight fraction of liquid. We're going to walk to this solid and reach that boundary. And that's going to give us a length that we've walked. So in walking from point B to that limit, we've now traveled distance S on the x-axis, which is also known as concentration alpha minus the bulk concentration value of 35. Okay, so there you see it represented here, maybe a little bit easier for us. S is our numerator. It's the distance of the segment of the tie line that takes us from the point of interest to the opposite phase of interest. Okay. Our denominator is the whole tie line's length. So we see that as the S value plus the opposite missing piece, which is the R value. Okay, so that is simply the limits of the x coordinates for the full tie line, C alpha minus C L. Okay, so similarly, to do this for the alpha phase now, to determine the weight fraction, so how much by weight as a fraction is these blue alpha solids, we are going to start at point B, walk to the opposite material of interest, so walk to the limit to the other material, so walk to the liquid territory, and we're going to measure that segment of the tie line. So that is component R, and we see that component R as our numerator this time. Okay, our denominator is the same, it's the full tie line length, and of course that was the C alpha minus CL again. Okay, so taking this approach, we're able to now determine how much by mass is blue particles hosted in the L. So let's use our numbers there to put that into context. So to determine WL, we knew we had to start from B. We're interested in the liquid, so we're going to walk to the solid. That is the longer component of the tie line, and that represents 43 minus 35 as our numerator. The whole tie line, of course, takes us from boundary to boundary, and that's 43 minus 32 this time, and that's our denominator. So the weight fraction of liquid in this material all of that green as it was, this is 0.73, or if you want 73% by weight of the whole specimen is in the liquid form. For the weight fraction of the alpha now, we start at point B, our material of interest, and we're going to walk to the opposite. So not to the solid, but now to the liquid. So it's the smaller segment here. That takes us to the 32x coordinate. 35 minus 32 is our numerator this time, divided through by the full tie line length of 43 minus 32. This gives us the complement value of 27%. So all of the alpha particles together sum up to give us 27 weight percent, or weight fraction, 0.27 weight fraction of the alpha phase. Okay, very good. So hopefully you can appreciate that these phase diagrams are very useful. They not only can tell us about what is the composition inside a subphase in a complex mixture, but how much of it is represented in the overall mixture in these two phase areas. So if we put that all in the same slide, I think we have that here. For point B, we know that the liquid is 73% of the specimen at point B. The liquid has a lower nickel content than the average, and that is at 32 weight percent nickel. The alpha solid particles that exist at point B are 27% of the whole sample by weight, and they are higher in nickel content, and they are 43 weight percent nickel. All right, hopefully you appreciate the use of phase diagrams and the tie lines to help quantify material